Hey everyone, let's dive right into this explainer and solve a massive mystery. Why do your single Lewis structures constantly fail you on test day? And how is resonance basically your ultimate cheat code? If you're prepping for a major chemistry exam right now, you already know organic chemistry can feel, well, like a completely different language. But resonance? Resonance is the grammar that actually holds the whole thing together. If you can master this, you unlock the ability to predict how molecules behave without having to memorize those endless, exhausting lists of reactions.
Here's our exact roadmap for today's revision session. We've designed this to give you the high-yield structure you need to absolutely ace those chemistry questions. We're going to hit 1. The resonance problem, 2. Key definitions, 3. Essential rules, 4. Core exam examples, 5. Chemical effects, and finally, 6. A quick exam revision.
Okay, Section 1, the resonance problem. Let's start with the fundamental issue here. The reality is, many molecules simply cannot be accurately represented by just drawing one single Lewis structure. You'll sit down to draw out the bonds, and sure, the math works out on paper, but then you look at the real-world experimental data and it completely contradicts your drawing. The bonds might act totally differently than a standard single or double bond ever should. So, to explain this bizarre behavior, we have to use the concept of resonance.
Now, if you remember just one single thing from today, make it this golden rule. Electrons move, atoms don't. Resonance happens when electrons, specifically your pi or lone pair electrons, move freely over adjacent atoms. The atoms themselves, they are locked in place. The nuclei do not budge an inch, but those pi electrons are delocalized. They spread out through overlapping p orbitals. And this spreading out is the absolute key to lowering the molecule's energy and making it incredibly stable.
All right, Section 2, Key Definitions. Examiners absolutely love testing your precise understanding of these terms, so let's get them crystal clear in your head right now.
This definition is absolutely crucial. Resonance is a phenomenon where a molecule can be represented by two or more valid Lewis structures. Just remember that these structures, which we often call canonical forms, are really just different ways to map out the electron layout on a piece of paper. Literally, none of these individual structures exist independently out in nature. They are purely a human attempt to pin down something that is, at its core, totally fluid.
Now here's where it gets really interesting. The resonance hybrid is the actual, real-world molecule. It isn't flipping back and forth between these different Lewis structures like a light switch. Not at all. It exists purely as this highly stable blended hybrid at all times. Think of a mule, right? It's a hybrid of a horse and a donkey. It isn't a horse for 1 second and then a donkey the next. It's just always a mule. The resonance hybrid is that true, real-world molecule.
So, what about resonance energy? Well, the crucial point here is that a greater resonance energy directly translates to a much more stable molecule. It's essentially the mathematical difference between the energy of the real molecule, our hybrid, and the theoretical energy of the most stable individual resonance structure you could possibly draw. A high resonance energy basically means the molecule is highly unreactive and very, very happy just the way it is.
But you might be wondering, why does this electron delocalization actually matter for the molecule's overall behavior? Well, before we start memorizing a bunch of rules, we have to ask why this spreading out is so vital to chemical reactions. It matters because it dictates exactly where the electron density lies. And in organic chemistry, let's face it, electron density dictates almost everything. It tells us where a nucleophile is going to attack, exactly how strong an acid will be, and just how tightly a molecule is going to hold on to its protons.
Moving right along to Section 3, Essential Rules. Let's lay down the strict, unbreakable rules you have to follow when drawing these structures so you don't throw away easy points. When you're asked to draw resonance structures on an exam, the examiners are actively hunting for violations of these exact principles.
So here are your 5 golden rules. Break any of these and, well, your structure is scientifically wrong. First, only electrons move. Atoms never move. Second, you can't just invent new electrons out of thin air. The total number has to remain constant. Third, you cannot magically change the overall net charge of the molecule. Fourth, every single canonical form you draw has to be a valid Lewis structure, obeying the octet rule wherever applicable. And finally, the number of unpaired electrons must stay exactly the same.
This quote right here brilliantly captures our one-line memory trick to anchor everything we're talking about. Spreading electrons equals molecular stability. When a charge is just confined to a single atom, it creates this high-energy, super-reactive hotspot. But by spreading that heavy burden across multiple atoms, the whole molecule relaxes. It drastically lowers its energy state. This is literally the entire driving force behind resonance.
Okay, Section 4, Core Exam Examples. Let's actually apply these rules to the specific molecules that are virtually guaranteed to show up on your exams. You really shouldn't be trying to figure these out from scratch on test day. You should already know their quirks inside and out.
First up is ozone, O3. This beautifully demonstrates how resonance creates equal bond lengths that sit right smack in the middle of a single and a double bond. If you just draw the standard Lewis structure for O3, you're forced to put a double bond on one side and a single bond on the other. But in the lab, tests prove both of those bonds are exactly the same length. Resonance is literally the only way to explain this intermediate bond character.
Next, notice how the carbonate ion handles things. It distributes its negative charge perfectly across 3 oxygen atoms, which results in a very specific bond order of 1.33. This is such a classic exam question. You've got a -2 charge perfectly shared by 3 oxygens. This massive delocalization makes the carbonate ion incredibly stable, which, by the way, is exactly why you see it absolutely everywhere in nature.
And then there's benzene. Benzene is literally the undisputed king of resonance. It derives massive stability from its perfectly equal delocalized ring of electrons. Its classical structure shows alternating single and double bonds, but frankly, that's a lie. All 6 carbon-carbon bonds are perfectly identical, intermediate in length. That's exactly why we draw that circle inside the hexagon. It represents that unbroken, highly stable ring of electron density.
All right, Section 5, Chemical Effects. Let's see how all of this builds into actual chemical applications, like acidity and basicity. This is where resonance stops being just a fun drawing exercise and becomes a hardcore predictive tool for chemical reactions.
Resonance can actually make a compound way more acidic by stabilizing its conjugate base, or it can make it less basic by tying up its lone electron pairs. Take acetic acid, for example. It readily gives up a proton because the resulting negative charge is so happily shared between 2 oxygen atoms, which increases its acidity. On the flip side, look at aniline. It's a pretty weak base because its nitrogen lone pair is super busy delocalizing into the benzene ring. That decreases its basicity because those electrons just aren't available to go accept a proton.
Now, exams absolutely love to test the difference between the resonance effect and the inductive effect, so do yourself a favor and memorize this comparison chart to lock in those easy points. The inductive effect operates entirely through sigma bonds, and it dies out really quickly over a short distance. Resonance, however, operates through pi electrons. It doesn't fade over distance as long as it's within a conjugated system, and it is a much stronger force when it comes to dictating the molecule's overall stability.
You're also going to need to instantly recognize which groups donate electrons into the system and which groups withdraw them. Positive R groups, like your alcohols and amines, push electron density straight into the conjugated system. Negative R groups, like nitro or cyano groups, suck that electron density right out. Knowing these groups on site is going to save you a massive amount of time when you're trying to predict reaction mechanisms.
Okay, home stretch. Section 6, Quick Exam Revision. Let's wrap this up with a rapid-fire review of the most critical, high-yield takeaways. Think of this as the ultimate checklist you want running through your head the night before the test.
Here are the top resonance-stabilized species. If you see benzene, the carbonate ion, the nitrate ion, the carboxylate ion, ozone, or the allyl carbocation on a test, your brain should immediately scream resonance and intermediate bond lengths. These are the classic textbook examples that professors use to build really complex questions. If you are ever asked to rank stability or predict a reaction intermediate, scan the molecule for these specific conjugated systems first.
For ranking questions, always remember this exact hierarchy. A resonance-stabilized carbocation will consistently beat a tertiary one. I know you've been heavily drilled on how stable tertiary carbocations are because of the inductive effect, but think back to our chart. Resonance is stronger. Delocalizing a positive charge over multiple atoms is always the winning move for molecular stability. No contest. If all else fails on exam day, rely on this fundamental truth of organic chemistry. Resonance equals stability. If you're ever completely stuck trying to choose between 2 reaction pathways or trying to figure out which product is going to be the major product, just look for the one that allows for the greatest delocalization of electrons. The molecule is almost always going to take the path that leads it to the lowest possible energy state. So once you master spotting a conjugated system, what other invisible chemical behaviors will you be able to predict? Resonance is really just the gateway. How much more of organic chemistry's hidden code will you unlock now that you can actually see how the electrons move? By deeply understanding this concept, you aren't just memorizing random facts anymore. You are literally learning to read the blueprint of the molecular world. Keep practicing those Lewis structures, keep tracing those pi electrons, and I promise you, those exam questions are going to start feeling like an absolute breeze. You've totally got this. Good luck with your revision.